Okay, welcome everyone. Good morning, good afternoon, depending on where you are. This is Benito Marcote from Jive, and I'm delighted to welcome you on behalf of the organizing committee of these online seminars sponsored by the European VLBA network. Today, we will have the pleasure of listening to Diego Alvarez-Ortega, who will actually tell us about the fully automatized VLBI calibration with VIPCAL, the pipeline that they've been developing. And before that, I would actually like to start mentioning just a few logistics before we begin. So you will be muted throughout the presentation, but then you are all invited to type in any questions you may have for our speaker, preferably through the Q&A section at any time. Or if you are watching us through YouTube, then you can put your questions in the chat. You can do it at any time. We will actually, after the presentation, we'll go through the questions, and then we will ask the speaker to go through them. At the same time, if you want to raise your hand, you're allowed, and then in the question section, you will be able to ask directly your questions or discussions that you may have. We will aim to get as many of your questions as we can, but we apologize in advance if your question is not among those that we have time to answer. We will try to keep the seminar to be within 1 hour. So if there are so many questions, we will need to be address only the first ones. So now, Emmanuel will now introduce today's speaker, Diego.
All right, thanks, Benito. So our speaker today, Diego Alvarez-Ortega, obtained his bachelor's degree from the University of Valladolid and his master's degree from the University of Cantabria, both in Spain. In 2002, he moved to the Institute of Astrophysics in Crete, Greece, to begin his PhD studies under the supervision of Dr. Carolina Casadiu. His research has focused mainly on the development of an automated VLBI pipeline, as well as its scientific exploitation within the Search for Milli-Lenses project. He is also an active member of the Polami collaboration, serving as a regular observer with the Aram 30-meter telescope in Sierra Nevada. Currently in the final year of his PhD, he will be presenting today his results on the automated calibration of large VLBI samples. So over to you, Diego, and yeah, we look forward to your talk.
Thanks, thank you very much. Let me start sharing slides. So could you please let me know if we are seeing the slides fine?
Yeah.
Okay, thanks, perfect. Well, thank you very much for the introduction, and thank you very much for the organizing committee of the EVN Seminars for the opportunity to present here our work. So today we are going to be talking a lot about very long baseline interferometry and its data calibration. So I wanted to start the presentation with a short, simple introduction on the topic. Very long baseline interferometry is an observational technique that combines the signal from multiple telescopes located in different places from Earth in order to achieve very high angular resolutions down to the micro arc seconds. We are talking about radio here in a range that covers more or less between 300 megahertz and 300 gigahertz. And the principle is as follows. Each couple of antennas, to what we refer as a baseline, observes the brightness distribution in the sky of a radio source. The signal at each of the antennas gets a timestamp, and then it's cross-correlated at a specialized computer, which we call the correlator. The result of this cross-correlation is a complex quantity that we refer to as visibilities. The relationship between the original sky brightness distribution and the visibilities is given by the Fourier transform. So what we do, but by combining all the visibilities from all the different baselines in the array, we are sampling the Fourier plane, and then later on we can reconstruct our original signal, our original sky, our original brightness. So what do we mean when we are talking about calibrating data for VLBI? Well, each of the antennas is affected by instrumental, geometric, propagation-induced errors that affect both the phases and the amplitudes of these complex visibilities. Data calibration is just the process of correcting these errors. The final goal is to obtain data that is coherent, both the amplitudes and the phases, both in time and in frequency, in order to later on average and recover our original signal. Here, what we are seeing in this short animation is the visibilities of a baseline, both amplitude and phases, as a function of frequency. And we can see how, as the calibration keeps on going on, the amplitudes and phases start to flatten out. This whole calibration process is a multi-step process, and I'm not going to go into detail to every of the steps. This will fill up lectures and lectures. But I would like to highlight what I believe is the most important step, or the one that is more characteristic of calibration in VLBI, which is the fringe fitting. Fringe fitting is our main tool to correct for any residual phases or any errors on the phase. It does so by looking at the delay and rate space. The delay is the derivative of the phases as a function of frequency. The rate is the derivative of the phases as a function of time. Again, the fringe fitting algorithm is complex on its own, but the main part, or one of the important parts, consists in doing a grid search in this delay and rate space and looking for peaks on this space. The peaks will give us the corrections we need to apply for the phases. And we will talk in this case about the signal-to-noise ratio of a fringe. Is the value of just dividing the height of these peaks by the floor of the noise. So through the talk, I will be talking multiple times about signal-to-noise ratio. Unless I mention it explicitly, I'm most of the time talking about this fringe signal-to-noise ratio. So how do we do this data calibration? Well, part of the process of the data calibration happens during the cross-correlation step, but the bulk of it is led to the final user, to the PI of the project. It requires a lot of expertise, both on the specialized software that is used for it. AIPS and CASA are the most well-known or the best-known ones. I mentioned here also PIM and HOPS. But it also requires expertise on the methods and the tasks and every step that has to be run. It is overall a very time-consuming step. For calibrating a single observation, it can range from, let's say, 1 hour for a well-behaved data set, if you really know what you are doing, up to multiple days for the trickiest of the cases. There are some pipelines out there that make this process easier. RPCAL from Michael Jansen, the VLBA run task, even the EVN pipeline. But they still require some human oversight, some supervision. They are usually based on an iterative process of running the pipeline multiple times until you can fine-tune the parameters. And they benefit, or we could say they require having some prior knowledge on the data. This makes the current pipelines not suitable for very large, very heterogeneous samples. And the whole calibration can become a big bottleneck for projects that involve such large samples. So after this super short introduction, I want to take a break from VLBI, and I would like to talk and introduce a bit the SMILE project, which is the science that has motivated the creation or the development of an automated pipeline. I guess most of us are familiar with lambda CDM. Lambda cold dark matter is the current paradigm in cosmology. If we talk specifically about cold dark matter, it has been very successful at explaining the large-scale structure of the universe. However, there are some discrepancies between observations and the theory, especially at smaller scales. There are many alternatives to cold dark matter. I'm mentioning a few here: warm dark matter, self-interacting dark matter, primordial black holes, but there are as many as you want to come up with. A way we have to discriminate between these different alternative scenarios for dark matter is because different dark matter models make different predictions on the abundance and the density profile of subgalactic low-mass dark matter halos. But, well, by constraining what is the abundance of these dark matter halos, then we can put constraints on different dark matter models. We could put constraints on different dark matter models. However, these are subgalactic dark matter halos. They are called subgalactic for a reason. We do not expect dark matter halos of these ranges of masses to form galaxies. So the question is, how can we explore these mass scales? Well, we can do so. One of the ways we can do so is through their gravitational effects, more specifically through gravitational lensing. Gravitational lensing is the distortion of the path of light due to the presence of a massive object. For example, in this case, if we have a bright quasar that is aligned in the line of sight with some supermassive compact object, the light path will get distorted, and for us as observers in the Earth, we will see two different images of the same object. The distance between the images depends on the mass of the object that acts as a lens, and also of the relative distance between the lens and the lensed object. For the range of masses that we would be interested to probe for the different dark matter models, let's say between 10 to the 6 to 10 to the 9 solar masses, the expected distances between the images is of the order of milliarc seconds. That's why we call such systems Milli-Lenses. And this is what SMILE is about. SMILE, which stands for Search for Milli-Lenses, is an ERC-funded project led by Carolina Casadillo, which search for these Milli-Lens systems in a large sample of high-resolution VLBI data of radio-loud AGNs. By constraining how many of these Milli-Lenses we can find, we can use these numbers to discriminate between different dark matter models. Even not finding a single Milli-Lens will already be very useful, and it will put some strong constraints, or will discard completely some of the models that I have mentioned before. And now is where I want to join with the issues regarding data calibration. In order for this search for Milli-Lenses to be statistically significant, it needs to be conducted in quite a large sample. For SMILE, we are talking about mostly archival, but also new VLBA data. VLBA is the Very Long Baseline Array, the US-based VLBI array. And here we have around 5,000 radio-loud AGNs, mostly focused on C and X band, 6,000 files, more than 600 projects, a total amount of more than 60 terabytes of data that span for more than 30 years. This cannot be calibrated manually. These current pipelines are, as I said, not suitable for this kind of samples, and this needs for full automation of the calibration, or hiring many graduate students, looking them in a basement and having calibrated data for, I guess, some years. In any case, this is the science that has motivated the development of VIPCALs. VIPCALs is a fully automated VLBI data calibration pipeline that provides end-to-end data calibration without any prior knowledge on the dataset. Calibration is quick, is robust, and something that I believe is very important, it's also reproducible. It has been implemented in AIPS using ParselTongue, a Python wrapper developed by Mark Ketenis. It's currently available on GitHub. There is a version that we keep on updating, and it can be run either on a local AIPS installation or also in any laptop in any machine using a Docker container. It can be used very easily through a very basic, easy-to-use graphical user interface built with the PySat6 package. Later, I will show a small demo of how it can be used. This is the whole calibration workflow of the pipeline. Don't worry, I'm not going to go in detail to each of the tiny steps, but overall we can say it's divided in 3 main blocks. There is a preloading block in which there are some sanity checks, different frequencies are splitted. There is a pre-selection of calibrators. Second block of loading the data into AIPS and doing some pre-calibration steps, retrieving missing calibration tables that can be found online, average data if desired or necessary, some smoothing, some clipping of the system temperatures, a choice of the reference antenna, and then it comes the main block, which consists of the typical amplitude and phase calibration workflow for AIPS for VLBI data, including ionospheric corrections and having as a final step a fringe fit on the target, either on the target or on a phase reference calibrator. So as I said, I'm not going to go step by step through every single point of the workflow, but instead I would like to highlight what some of the automation features that make VIPCALs different from the current pipelines that are available. First, as I mentioned at the beginning, there is a pre-selection of the instrumental calibrator. So when we are working with archival data, most of the cases you are only interested in a few of the sources that are contained in the dataset. And it's not rare that datasets can account for hundreds of gigabytes, even a terabyte. In order to speed up the process, what the pipeline does is looks for potential calibrators using the source list of the dataset and cross-matching it with the VLBA calibrator list. This speeds up the process by orders of magnitude. Another very useful step, as I mentioned, is the retrieval of calibration tables. It works for VLBA, both VLBA and EVN experiments. So especially for people that have worked with older data might know this. there are many relevant tables or many relevant metadata that is necessary for calibration, the system temperature of the antennas, the gain curves, some flag information, that even though in the newer data is usually attached to the FITS files, in previous datasets you need to retrieve it manually, look for it, and attach it a posteriori. This is done automatically by the pipeline, again, super useful for all the data. There is an automatic selection of the reference antenna also. This is a rather simple algorithm. Is based on the availability of the antennas and on their signal-to-noise ratio, fringe signal-to-noise ratio. So here in this example, for example, we can see that for a VLBA observation, Mauna Kea has been discarded because it was not available in all of the scans. Brewster, North Liberty, and Croix are not considered because they are not part of the centralmost part of the array. And then for the rest of the antenna, there is the rest of the antennas, there is a prioritized list based on the signal-to-noise ratio that we have computed. In a similar fashion, we can make a baseline-based selection of which scans and which sources are going to be used to calibrate for instrumental effects. And also, among other things, there is some optimization done at the final fringe fit. There is an optimization of the solution interval that is used for it. And the pipeline also explores whether single band or multi-band fringe fit will be better for the current dataset and for the case we are using. So here I have a short video showcasing a bit how the pipeline can be used. As I said, the interface is very simple, minimalistic. It has many options that can be used in case you have prior knowledge of the dataset, but in the video we are going to see the simplest way of using it with the bare minimum input, which is the FITS file, the folder where you want your outputs, and the name of the target you want to calibrate. Actually, you would not even need the name of the target. You could calibrate the entire dataset. Once you click continue, it takes you to this next screen in which it reports a log of each of the tasks that are being carried out. It keeps a track of the flags, of the visibilities, of the scans that are being used, and at the end, it exports the data and produces plots. The pipeline also has some very basic, very simple plotting capabilities to have a quick look of what is the quality of the finally calibrated dataset. Some of them also allow you to iterate over different baselines, different calibration tables, different scans. As I said, it's very basic. It's just for a quick look of the quality of the data that we are dealing with. Here we can have a better look or a more clear view of what are these screens or what are these windows with the log and the different plots that I was mentioning, amplitudes and phases as a function of frequency, as function of time, as function of the UV radius, also the UV coverage. In any case, once the pipeline has completed its calibration, it will also produce the log in a text format. It will produce the previous plots and more plots in a PDF format. And well, of course, it will deliver also the calibrated UV FITS file and all of the tables that have been used for the calibration. Now I would like to talk about a paper that we published recently in which we test and we validate VIPCALs. Because the main idea when developing VIPCALs, or VIPCALs has been developed, let's say, with SMILE in mind, we decided to validate it on a subsample of SMILE. We selected 1,000 sources, which accounted for 1,400 VLBI observations, in the sense that one source might have multiple frequencies, so that each frequency will count as an observation. Again, a large sample, thousands of files, hundreds of projects, close to 20 terabytes. In order to make the test and the validation as fair and complete as possible, we organized the sample in the following way. We took 900 sources that had at least C or X band data, because it's the one that we are interested the most in SMILE. This is so because it offers a compromise between the resolution and the quality and the overall behavior of the data at these frequencies. So 900 sources that had at least data in these bands. 450 of them, they were uniformly distributed in flux between 50 millijanskis and 1 Jansky. The other 450 sources were uniformly distributed in exposure time between 1 minute and 1 hour. For completion, we also added another 100 sources that had at least data in U and K bands, just to showcase that the pipeline can also work at slightly higher frequencies. This is the final distribution of the frequency bands. These are some of the histograms and plots for the different 3 subsamples. About the performance, the pipeline VIPCALs was able to complete all steps of the calibration process for 1,372 datasets out of the 1,400 total observations. It took in total 7.5 days, which accounts more or less to around 10 minutes per observation. This was running a server, but I would like to highlight that it was done using a single core. Why so? Well, when we did some profiling of the code and we computed the time that had been spent in each of the steps during this test, we realized that more than 50% of the data is spent on the data loading and on the plotting. And this points to the read and write speed of the disks that we are using as the main bottleneck of the pipeline. Thus, we decided to not invest or to not dedicate much more time into the parallelization or parallelizing the code, although it could technically be done using ParselTongue. Here in this plot, we can see a bit about the results of the calibration. In this plot, we are seeing the visibility ratio as a function of the different steps of the pipeline. The visibility ratio is defined as the number of unflagged visibilities divided by the total number of visibilities. This is a simple visual way to see at which steps of the pipeline we are losing or we are flagging our data. There are three distinct steps or regions, which is what we could expect. One of the points where we are flagging visibilities is during the instrumental delay correction. This is associated with datasets in which there was not a bright enough calibrator for the instrumental delay correction, or a calibrator that was not available for all of the antennas at all times, or with not good enough coverage. There is some drop in the number of visibilities during the bandpass. This is also to be expected when we are working with VLBA data. Because of the way the reference frame is set up in VLBA observations, during the bandpass, the outermost channels of each of the bands are flagged. So this is inevitable. So depending how many channels you have in each of your bands, you will have a larger or smaller drop in the number of visibilities. And finally, and as I was mentioning or introducing at the beginning of the talk, is this step, the fringe fitting, the one that decides if your data are there, if there has been a detection, if your data is good enough to find a fringe. We are using a signal-to-noise ratio of 5 here. So if we look more closely to the fringe fitting step, we can see that on average for any given data set, the task fringe in AIPS, the fringe fitting, is giving close to a 90% of good solutions or solutions that have a signal-to-noise ratio over the threshold of 5. When we look at this plot where we have the relationship between the flags, the observing time, and this fringe ratio, again, a fringe ratio is how many solutions over the threshold you have gotten out of the total possible solutions, we can see there is a correlation between the low fringe ratios and the flags. So less flags, more unlikely it is for the fringe fitting to find any detection. Interestingly enough, there doesn't seem to be any correlation with the observing time. When we manually inspected these datasets in which the fringe ratio was very low or the fringe task simply failed, in most cases it was looking or it was pointing towards simply just a non-detection of the source. And this can be a problem in evaluating the performance of the pipeline because it's very difficult, or I would even say impossible, to disentangle the quality of the calibration process itself with the quality of the dataset that you are working on. So in order to test the pipeline, we decided that the best course of action, the best way to go was to compare VIPCALs with data that had been calibrated manually. Here I'm showing results from an upcoming publication from another PhD student in our group, Avinash Kumar. Avinash has developed another pipeline, again, a not fully automated pipeline, same concept, same idea as VIPCALs, the same project, but now developed in CASA. This pipeline is called Avica, and here we are comparing the results of the calibration of Avica, VIPCALs, and data coming from Astrogeo. Astrogeo has huge collection, archive of thousands, tens of thousands of manually calibrated VLBI data done by experts. So what we did is we chose 3 sources, trying to have some variety on the fluxes and the exposure times. We calibrated them, and then we averaged the data per scan. We average the data in frequency, and what we are seeing here are the histograms with the number of detections as a function of the signal to noise of these detections. What we can see here is that in the three cases, the histograms are comparable, if not equal. We have repeated this analysis for another 10 sources, and we can say that, well, we are seeing the same results. And we can say that, at least in most cases, the automated calibration by both AVIC and VIPCALs, they are compatible, or they are as good or even the same as data manually calibrated by an expert. However, I said at the beginning, the pipeline has completed all the steps successfully for 1,300 something out of the 1,400 total data sets that we try to calibrate. There are some cases in which it failed, and we have looked at them manually, one by one. All of them are quite minor. They could be solved with some small adjustments to the workflow, and we have classified them in these 4 groups. There is the issue of when the datasets do not include the calibration tables. I'm talking about system temperature, gain curves, flags, and they need to be retrieved online. In some cases, the tables are simply not available. In some cases, they require some heavy manual editing. There are typos, there's information that is missing. We were struggling also with setups in which the IFs, the intermediate frequencies, the sub-bands, were not ordered in frequency. AIPS cannot deal easily with them, but this could be solved with, again, some adjustments in the workflow. We were having issues also in the cases where subarrays were involved, because this was interfering in a way with the algorithm for selecting the reference antenna. And in just 2 cases, we found there was some issue with information regarding the order of the visibilities in the header. Again, very minor. But I would also like to say that there are other limitations that come from the fact that this pipeline has been designed, or the main objective was to work on SMILE data. So this pipeline works, but it works for total intensity data, continuum, centimeter wavelength, and it has been extensively tested only on VLBA experiments. The code will require it's going to require some fine-tuning in order to adapt it for other arrays. In order to progress with the pipeline and try to make it valid in as many cases, as many scenarios as possible, at this stage, the expertise of the VLBI community is fundamental. So now in this part of the talk, I would like to talk a bit and, again, showcase some of the cases in which we are using VIPCALs in our group. So I would like to start with the full calibration of the SMILE sample. We published the paper with the validation of this subsample in November, and now I'm glad to announce that we are pretty much done with the full calibration of the entire SMILE sample. So these are the numbers, very big numbers again, 60 terabytes of data, 90% of the 5,000 sources have been calibrated. The cases where we could not calibrate are the known issues that I have described a couple of slides ago. We have produced 8,000 calibrated UV feeds files. This is, again, as I said, because one dataset could contain multiple frequencies for the same source. The total output of the pipeline was 260 gigabytes, including the calibrated UV feeds, the tables used for calibration, all the plots and the logs from the pipeline. And this has been done in a total of 780 hours, 32 days and a half. About the quality of the data, we can say that close to 90% of the observations had more than 50% of their data going over this threshold of 5 in the fringe fit, during the fringe fit. So these numbers are very big, but I would like to give a bit of context of what is the importance of this. So we are going to go with a bit of trivia. The combined archive of the East Asian VLBI network and the Korean VLBI network in its full operation period, which has been for the last 12 years, contains, I'm going to give you a few seconds to think the answer. I will take the chance to take a sip of water, actually. So the full archive of these 2 arrays contains a total of 55 terabytes of data. SMILE has processed a similar amount of data with VIPCALs in only 32 days. And I want to emphasize, using one single computer, one single core, and only one person dedicated to this project. And the person didn't go insane on the process. Important, I would say. So this opens the door to the systematic calibration of archival data. As an example, I want to show what we want to do with SMILE. Upon completion of the SMILE project, we are going to deliver all the calibrated datasets alongside with images and multi-wavelength information on the sources, redshift, light curve, images. This is an example of the catalog that we are preparing, in which all the information of the source has been retrieved automatically. Achieving something like this for any of the major VLBI observatories would be a huge achievement, will be very useful for the overall VLBI community, but also, I believe, it would make VLBA science much more accessible to the broader astronomical community. Another cases in which we have been using the pipeline is for the follow-up of interesting sources. Going again to the Milli-Lens candidates, through the project, we have been able to identify some promising candidates for this kind of systems. Using VIPCALs, we have been able to do a multi-epoch, multi-frequency study of the 9 most promising ones. This implied the calibration of 144 archival observations, both VLBA and EVN data. And this gave us a very easy and very quick access to maps for kinematic studies, very complete spectra, and very complete light curves. Another case, J1048, a very interesting blazar. It's a blazar that shows a peculiar periodic, quasi-periodic behavior that can be seen at multiple wavelengths. There are currently 2 competing hypotheses of why this could be, what could be producing this. Maybe it could be due to the ejection of new components in the jet, or it could be due to some precession movement of the jet. Using VIPCALs, what we have done is first identified all archival data that was available both for VLBA and EVN, are all of these vertical lines that you can see imposed over the light curve. And we have used VIPCALs to analyze and to calibrate and analyze all of them, more than 100 datasets, in order to study the position angle of the jet of this source. This, a work that would have taken months, if not years to done, has been done in a record time using automated calibration. So approaching to the end of the talk, I would like to discuss a bit what is the direction that we want to take with the pipeline, what is some of the future work. As I said, it could be one of the main goals would be to expand its use or the cases that it can be used, and that goes through testing it extensively also with other arrays. This will imply some slight adjustments due to different metadata, presence of subarrays, more heterogeneous arrays than the VLBA. We will need to change or modify slightly some of the workflow and the algorithms. Another capability that would be a good improvement, a great improvement for the pipeline, would be the automatic flagging, or allowing allowing VIPCALs to automatically flag very obviously bad data, both in frequency. For example, here we are seeing again amplitudes and phases as a function of frequency. And we can see this thing over here is an artifact produced during the bandpass calibration, and that it really messes with the overall amplitude of the baseline of the visibilities. It should be very easy to remove. We also want to do it in time. Here we are having a look at the amplitudes of a baseline as a function of time. It's a baseline that includes the VLA, and these were moments where the VLA was auto-phasing and it was not producing data that were useful for VLBI. Again, we should allow the pipeline to remove this very evident, very obviously bad data. Another step that would be interesting to add, and it's very relevant when working at higher frequencies, going from centimeter to millimeter, is to implement opacity corrections when there is only weather data available. Opacity measurements can be, even if they are not provided by the observatory, they can be inferred or they can be fitted by using the system temperatures and the measurements of the temperature of the atmosphere. However, this works very well when your coverage of the system temperatures as a function of the air mass is complete enough to properly fit the data, like it is this case. When working with archival data, or at least it has been the case for SMILE, it's very common that we find ourselves with cases like this, where there's pretty much nothing to fit. What we are working on now is to, on a way to assess what is the quality of this fit, to at least inform the final user. This has been the opacity correction that has been done, but this is the confidence with which we are doing it. And finally, I would like to address a question that I assume some people on the audience might have. Okay, you are calibrating a lot of data, but what happens with the imaging? If there is any non-VLBI expert that has survived until this point of the talk, I'm going to make a short summary of what is the imaging for VLBI. Imaging on itself is another whole issue. Because we have an incomplete sampling of this Fourier plane that I was mentioning at the very beginning introduction, the reconstruction from the Fourier plane to the original brightness distribution becomes an ill-posed problem. This means that there are infinite mathematically valid solutions. There are many images that could fit our visibility data. There are multiple algorithms to do this process. The process is still highly manual, and it represents, again, a big bottleneck when working with such large samples. We are aware of this, and in our group, there's two people. There is Felix Potzel, Alejandro Mus, that are leading a study to assess what is the current capabilities of automated imaging. For the needs of SMILE, it needs to be robust, but it also needs to be time efficient. The way they are doing is by testing multiple algorithms. I'm mentioning a few here: clean, RML, wavelets. And they are doing it on a huge library of simulated data, more than 100,000 datasets that have been simulated in a realistic way, using as a baseline or as a guide the data that we have calibrated with VIPCALs. Stay tuned for the results. It's going to be a very, very interesting study of what are the capabilities of today's imaging algorithms. And this is just a summary. I'm going to finish here of a summary of what we have been discussed. Current VLBI pipelines are not scalable or not suitable for large heterogeneous samples. Large projects like SMILE requires for fully automated calibration. We have developed VIPCALs, which delivers end-to-end data calibration without any prior knowledge on the data. The calibration is very quick, it is robust, and I want to emphasize this, is reproducible. We have successfully tested on VLBA data, both in the test sample that I presented on the paper, but also on the totality of the SMILE sample. However, the current version is suitable only for SMILE. It's been tailored for full intensity, continuum, and centimeter wavelength data. In any case, VIPCALs opens the door for the systematic calibration of archival data. However, in order to progress and to expand the use of the pipeline, I would like to call for the feedback. It's very, very important, the feedback and the expertise of the VLBI community. Once again, I would like to thank the organizers for inviting me and for the opportunity to talk about my work. I would like to thank everyone for your time, and I think this is all from my side. Thank you very much.
Thank you very much, Diego. It has been fantastic summary on the pipeline, and definitely great to see all the results and what you can do. So I think there's a lot of people that will be interested on this, including us, I must say. So yeah, with this, we have time, and then we open the floor for interesting questions that people may have after your talk. I will remind her that you can raise your hand if you want to ask directly to Diego, or you can write your questions, things that you want to discuss, either in the Q&A here in Zoom or in the chat in YouTube. Yeah, so first, Manuel.
Yes, thanks very much, Diego, for such a nice talk. So from what I understood from your talk, the pipeline is built on ParselTongue using AIPS. Yeah. So, but is there any plans to have like maybe a CASA version? I mean, as you probably will be aware, radio astronomy in particular, gradually we are moving towards CASA to have CASA do most of the calibration and imaging and stuff. But is there any plans to make a version which is usable in CASA or works underneath CASA, something like that?
Yeah, thanks. So not for VIPCALs, but we are aware of what you are saying. And for SMILE, because all of this process is being done automatically, it was very important for us to cover the different types of software to be completely sure that the calibration would be as robust as possible. That's why this other student, Avinash Kumar, has developed or is developing the Avica, which is a similar pipeline. It's not a port of VIPCALs. Avica is built on top of RP card, and it makes it work in an automatic way in the same way as VIPCALs. So it will fulfill the same role as VIPCALs in this case. But nowadays you cannot make everyone happy. There will always be the AIPS community, there will always be the CASA community. So we decided to go with both approaches. They are not the same pipeline, but they fulfill the same purpose.
Okay. Yeah, thanks for this. And maybe just not a question, but a quick follow-up if I have the floor, Benito. Yeah. So Jack Radcliffe is leading this commensal survey where you try to correlate VLBI data. Usually when PIs propose for time, they have target of interest, but the instrument has a field of view where there'll be other sources in the field of view, and the idea is to sort of correlate the data within the entire field of view for any single observation, which I think your pipeline will be very handy. So maybe you can get in touch with Jack or Benito from the observatory point of view when this project goes live, and then you can help calibrate, the entire field of view for data and stuff like that. I think it's really good. Yeah. Thanks.
Yes, thanks. I'm aware of the work they are doing. I have not had the chance to talk with Jack, but I would love to. I think it would be an amazing idea. It would be the best way to make the best out of our data. But thanks for the comment, really.
Yeah, and if someone else wants to make a question. Meanwhile, I was interested in something that you mentioned of what you've been doing with EVA and KVN data, because it's something that we've been already discussing, and some people was interested to do it with the whole EVN archive. It's really extensive. We have all the data. And then it was something that from time to time was coming, and then will be really interesting that we had in our minds to be able to provide some results, basically what you already did there. So it's something that we can actually talk in the future, because it will be definitely interesting to have the archive with all the information or as accurate as possible. And it really overlaps what you've done with what we had in mind at some point to do here.
Yeah, I would also like to take the chance now and say that one of the issues that we faced when working with such a huge and large sample was simply retrieving the data or downloading the data. So I would like to encourage for anyone that can work on this or has any word on this to also implement features that allow for scripted or bulk downloaded of the data, because delivering the information would be amazing, as what you have just said, Benito, but access to the data is still tricky these days. So I will take the chance to also make a call for help in that aspect.
Yeah, I can talk just on the EVN side because I faced something similar. We have different observations to analyze. And then currently, I know that from the EVN we will change the archive to some extent, but then one of the things that we will definitely want to preserve is like you can scrape and download it by just knowing the project codes that you are interested in, that you can search from calculators or sources. But then that should be definitely the only information that you are required, and then you will be able to retrieve all the data that I think the VLBA allows you to do that too. But then, yeah, as you mentioned, not all observatories do that. And then if you want to do it in a large number of observations, this is really tricky.
Indeed, yeah.
Okay, someone else, some questions we may have for you? If not, I may have one, like how it's the imaging part in VIPCAL. Like as you mentioned, there is now a lot of approaches and then verifications to see which methods can be good or so. But then in your case, what's the major limitations that you've seen, or how you found this working in a more automatic way for all these calibrators?
So, well, the imaging is going to be independent from the pipeline, because at the end of the day, everyone has their own preferences, everyone has their own science cases, and they would like to choose one flavor, one algorithm for the imaging or another. The main limitation again, will always depend on your science case and what is the sensitivity you want to achieve, what is the resolution that you want to achieve, what is the kind of sources you want to image. I would say that for now, an automatic stopping criteria for clean seems to be the most promising, in the sense that clean might strike the balance between getting good enough images and doing it in a time that is not prohibitively expensive or computationally expensive. But it's still a work in progress, and it's a broad field indeed.
Yeah, indeed. So I think, sorry, if there is no more questions, we can thank Diego really for the great summary. It's really good to see this kind of seminars and all the details that it's hard to find otherwise. Oh yeah, we have before one question from Thomas. Global VLBI often has subarrays, which require changing the reference antenna. How do you deal with it actually?
It does not deal with it at the moment, but the way would be to just implement some slight changes on the workflow. So the only problem would happen regarding the selection of the reference antenna that you are using. So right now, the pipeline, it's too strict in that aspect. With some rather small adjustments, we would just allow for the possibility of having multiple subarrays. Another problem is that, at least in the VLBA data, with the metadata, it is not explicitly detailed which scans belong to one subarray or the other. So we will need to come up with an algorithm. It can be done. It just needs to put some time into it, that will identify which scans belong to each subarray or what subarray was observing in each of the scans. And then the workflow could be very easily adapted into it. It's not a major wall for the pipeline. It's just something that we have not thought of because of the project, the kind of data we have been dealing with.
Yeah, thank you. And then we have a question from Anya. Do you plan to extend the work for spectral line data in the pipeline?
Well, I don't know how feasible it is. I do not have the expertise on working with spectral line data. I understand that some of the complications might come for selecting certain lines that have to be used as references during the calibration process. But I would love to talk with people. So I understand not many questions, for people not having many questions now, but I would really like to encourage people to have a look at the pipeline, try to run it on their data. It will likely not work. Reach out to me, let me know what is the science case you want to address, let me see what are the issues you are finding, let's see how we can address this. Spectral line, why not? It's very difficult for one person or one single group to try to cover every single science case or use of VLBI. So I would really love to hear from the community. I would really love some feedback of the different groups on in which cases do they think an automated pipeline could be useful. So spectral line people, please reach out to me. I would be very interested to know on how we can proceed with the calibration, automatic calibration for those cases.
Yeah, and I think one important point there is like, it's in GitHub, it's open source. So as you said, one person cannot develop for everything. Like this one, definitely you develop it for your science case. But then I think the most important part is like, if you do a spectral line or any other kind of approach analysis, it will be good to actually, start using or getting in touch. So you don't need to build most of it. Like most of the steps, as far as I know, even if I'm not expert on spectral line, are identical. So they are just, let's say, a couple of different steps in the middle for the pipeline to work on spectral line, which means that you can reuse everything that is already here, just adding some features for that particular cases. And it applies for most of it. So it will be good to actually start narrow down in the community. As we mentioned, we've been already talking that hopefully in the near future, we should move to do some workshops and integrate the people that are developing pipelines like Diego. And then try to do that. We don't need to reinvent what has been developed here and some other parts in other pipelines. And then maybe it's good to start integrating that one with the efforts or everyone. So if they're spectral line people, they just can focus on what is needed in the spectral line and then forget for everything else because it's here, let's say, for example.
I completely agree. Really, really agree.
And yeah, if that's it, I think this has been really interesting and insightful seminar. So we will just finalize with one advertisement that Emmanuel will give on the EVN symposium and users meeting. I hope you're seeing my share screen.
Oh, yes, there it is. Yeah, thanks, Benito. Yeah, so just a reminder that the 17th EVN Symposium and Users Meeting will be happening in Manchester this September. If you have not registered, please do so. There are still spaces available. Please register before all the spaces are taken up. And I think there's going to be quite a lot of exciting things as part of this EVN Symposium. I mean, obviously, all the symposiums have been very super exciting, but this year we are having something special for all attendees or participants, which I'm going to keep it as a secret. Be in Manchester in September, and then you can experience it in full. Yeah, so that's what I can say. And yeah, registration is still open, so please do register as soon as possible.
And actually, on that note, the week before the EVN Symposium, it will be the Aries School. Sorry, I don't have the slide on that. But then there will be the Aries School the week before in Italy, in Noto. So if, especially if you're new on the VLBA world or you have students that will be involved on data reduction, not only VLBA, but the whole radio astronomy, then it's a really great place to actually learn how to analyze data and radio data. And hopefully we're still, I mean, the registration is completely open right now. We're still, they are still finalizing the programs, but then hopefully we'll be able to use some of these pipelines actually here or in the future there. So you can actually get some hands-on on actual data and then learn how to analyze all these observations. So with that, thank you, Diego, again for the really nice seminar, and thanks everyone for joining us. For now, we will do a stop for summer already, and then in September we have the EVN Symposium, as Emmanuel said, so most of the topics that we cover here will be already there. And that means that the EVN seminars will resume likely in the fall, in October or November. So thank you, everyone, and see you next time.